We are going to repeat the same ordinary least squares method, but now we are going to use uh, the criterion function minimization issue here. Okay, so everything is standard, and I just included 1 over 2 for simple algebra. At first, I'm going to derive the derivative. So Li was, excuse me, 1 over 2 yi minus xi transpose beta, Li beta squared, okay? And its first derivative is minus xi times yi minus xi transpose beta. Okay, and second derivative is xi transpose, that's it, okay? Pretty simple. And then we did the first one, show that beta 0 is the unique minimizer of the expectation. Let's see, expectation of Li beta is 1 over 2 expectation yi is xi transpose beta squared. And I'm going to check the first order condition and the second order condition. So let me check the second order condition first. Oh, because we already calculate the second derivative already. So the second derivative of the population criterion function is expectation of xi transpose. And we know this is strictly positive definite. Using the lemma, right? I mentioned it like in the class. So when expectation x prime is invertible, because the matrix is by construction weakly positive definite. So if you add invertibility assumption, then it becomes strictly positive definite. So second order condition is satisfied. That's good. Now the first order condition becomes expectation xi minus expectation xi yi minus xi, this one. So if you plug in beta 0, then it becomes minus expectation xi ui, so it is 0. So beta 0 satisfies the first order condition, right? It is either like a maximum or minimum or local minimum maximum. So, and then together with the second order condition, it is strictly positive definite. So beta should be the unique minimizer, right? So that's the second thing. And omega is expected value of beta 0 times beta transpose. So this is like there are two minuses, so they will be cancelled out. We get, so the first part is xi times yi minus xi transpose beta 0. This is the first guy. And the second guy is the same thing, xi yi minus xi transpose beta 0 transpose, all right? But y minus x prime beta is scalar, so they are not affected by transposition, and each term is ui. So we will just pull them out of the transposition, and we get xi transpose. This is omega, right? The familiar form. We did part C and part D. So easy. H is defined as second derivative at beta 0, but we saw that the second derivative does not depend on beta. It's like this, and by the assumption it is non-singular, so nothing more to do. And this is the annoying part. Here it should be beta. Assume that beta is bounded, and then we need dominate the second derivative. It is so obvious again. Supremum of over beta of xi transpose, right? So think about this. This is second order derivative. It does not depend on beta. So there's nothing to take supremum, right? This is just this guy, okay? So, and then if xi transpose norm is finite, then we get the desired outcome. So this is also simple. And derive the limiting distribution of beta hat. So then, so far, we collected all the sufficient conditions. Sufficient condition first, beta 0 is the unique minimum. And second, beta 0 is bounded. So it is compact. And third, Li is twice differentiable, which is trivial by the functional form. And number 4, dominate the second order derivative, right, which was also satisfied. And 5, H0, which is expectation of the second order derivative at beta at the true value, is non-singular, proved it. And 6, omega is first derivative times first derivative at true beta, right? This was the sufficient conditions for asymptotic normality. And then under these assumptions by lemma, we get normal distribution with V, where V is H inverse omega H inverse. And H inverse is here, remember, H inverse, H was expectation x prime, we calculated, and omega was expectation u squared x prime. So then we get the same familiar sandwich formula. Okay, so and the final question is, the final part is, how can we calculate the standard error? Exactly same as the first question. So I'm not going to show you.